Godot 4 beta dropped, you know what that means?
We get automatic mesh LOD.
Or maybe the much better physics system?
What about the brand new Vulkan renderer?
What? No, who cares about any of that nonsense? We got compute shaders, baby! I was looking for a way to explain compute shaders to my viewers, but then I thought, ray tracing. So I did it. I made it. I posted it on Twitter so I can pump my brain with some of that juicy dopamine. It does better than any tweet I've ever posted. Have a panic attack, but it's fine. Just hop onto Fabian's stream and let's relax a bit, right?
Yes, Nekoto, you're gonna go back to ray tracing now, because I'm looking forward to that video too.
You should feel pressure. You should feel pressure.
God damn it, Fabian. Well, you can call me Ace Roller because my ray tracing is going to give you a ball. You see, ray tracing is actually a pretty good way to learn how compute shaders work and where to use them. A compute shader computes stuff. I know, amazing explanation. That computational task could be anything from procedural map generation and erosion to ray tracing algorithms, as we will later find out. The main difference with a compute shader is that it actually has no purpose unless you give it one. For example, a vertex shader is responsible for transforming vertices between multiple coordinate spaces and modifying them as needed, while a fragment shader serves to texture meshes and calculate their output color on screen. This is why vertex shaders and fragment shaders are part of the rendering pipeline, but compute shaders sit outside the rendering pipeline and only do things you tell them to. Do not forget, however, that they are shaders, meaning they can leverage the entire power of the GPU. But we're getting ahead of ourselves. Why bother using a compute shader in the first place when we can already calculate anything we want on our CPU? Well, I'll tell you. Imagine you have a screen with 1920 by 1080 pixels, which is around 2 million pixels in total. And let's say you have to calculate a color for every pixel on screen. Since most CPUs have around 8 threads, best case scenario, you can only process the colors for 8 pixels on screen at any given point in time. You know how many cores the GPU has? Thousands! GPUs can crunch through any task that can benefit from parallelism. Say for example, I don't know, maybe tracing a ray for every single pixel on screen? Shit. Before we get into ray tracing theory, let's run over how compute shaders work. They execute in work groups. You can imagine these as a 3D stack of computers that are each defined by their X, Y, and Z coordinates in the stack. Very, very important note. None of these work groups can communicate with each other, and they are executed in a random order, so don't rely on sharing information between them. Now, inside each workgroup is another 3D stack of threads called invocations. These can communicate with each other and they are all processed simultaneously. Again, the invocations are identified by their 3D coordinate in the grid, which is called the local invocation index. However, they can also be identified globally by their position in the workgroup, plus the position of the workgroup itself, which is called the global invocation index. Keep in mind that you ideally want your invocations to be a multiple of 64. This is because of the way invocations are dispatched by the GPU. Okay, just ignore whatever I'm saying here. The text on screen is actually what's correct. That idiot who recorded the audio is incorrect. He swapped around the numbers, so just ignore him. NVIDIA GPUs like multiples of 64, while AMD GPUs like multiples of 32, and 64 is also a multiple of 32, so that works pretty well. So for example, a good invocation size could be 8x8x1 for 2D thread groups, or 4x4x4 for 3D thread groups. To start out a compute shader, create a new .glsl file and place these two lines on top. The first indicates to Godot that this is a compute shader, and the second defines the GLSL version we're using. Much like my will to live, inputs and outputs for compute shaders are non-existent. You have to define the inputs and outputs yourself. You can receive data into the compute shader and write out data from the compute shader using shader storage buffer objects, or SSBOs for short. If you used vertex and fragment shaders before, this is basically like a uniform that you can also write data to. The layout qualifier is what we use to define these buffers. Set 0 means that this is part of the first uniform set. Binding 0 is basically the index of the buffer within the set, since you'll most likely have multiple buffers in your shader. Don't panic, STD430 is not a sexually transmitted disease, it just tells the compiler to follow the layout standard that was introduced in GLSL version 4.3. Restrict, read only, and write only are memory qualifiers that allow the compiler to optimize the usage of this data across invocations. There's a link in the description if you want to learn about all of them and when to use each of them. Inside, we define all the data that this storage buffer will provide, similar to a struct. There is one rule you must follow though. Each storage buffer object can only have one variable size array, and that must be the last variable inside the storage buffer. If you need another variable size array, you need to define a new storage buffer. Finally, create a new void function called main. This is going to be where the entire logic of your computator goes. Of course, writing what goes here is entirely up to you. You can read and write data to the storage buffers as needed. Right above the main function, we will write a new layout qualifier that defines the number of invocations this shader should be run with. Remember that the invocations are decided by the shader and the workgroups are decided by the dispatcher, which is GDScript in our case. I would also recommend reading up on the atomic functions that are provided to you since you will be working in parallel. Of course, as the saying goes for parallel computing, there be dragons here. Cool, you now have a bunch of storage buffers in your shader, but you still need to actually pass in the data that you require from GDScript into your shader. First, let's set up the compute pipeline, which is done using the rendering device class. This may look complicated, but all we're doing is loading up the GLSL file, compiling it into SPIR-V code, which is used by Vulkan, and then attaching it to a rendering device pipeline. At the end, we run this bit of code that dispatches the compute shader, specifying the number of workgroups to be run, and then we wait for the GPU to finish executing the compute shader before we start reading back information. In between, we define our shader storage buffer objects, which we will write data to and receive data from. These are the same as what we defined in our shader. This code defines a new shader storage buffer object, and then we use the addID function to add any data to the storage buffer if we need to, suppose this is an input. All the data must be passed as bytes, so you'll need to manually encode them into packed byte arrays yourself. Also, a useful trick is that the packed byte array's size method actually returns its size in bytes, so you don't need to calculate the number of bytes yourself when defining the storage buffer. However, if you do need to calculate the bytes yourself, just remember that by default all the values in the shader are 32 bits, which is 4 bytes in total, which includes both floating point values and integer values. All other data types in the shader are just a composition of these base types, like a vec4 is just 4 floats, which is 4 into 4, 16 bytes. Now you know how to set up, run, pass data to, and read data from a compute shader. You know what that means? Let's get to the juicy part of this video, the ray tracing. Now, I cannot take any credit for any of these algorithms. Frankly, I'm too stupid to know how to make this stuff. I just learned them from the wonderful Raytracing series I have linked in the description. I've just done the Godot plus GLSL implementation of them. Now, a ray is basically an object that has two components, an origin and a direction. In order for us to draw objects on the screen, we need to shoot out a ray for every single pixel in the direction of the view vector. To figure out the ray direction, we need the camera's global transform and the camera's projection matrix, which we then use to construct a perspective ray. Godot has this cool feature where it does not allow you to retrieve the projection matrix. They have a built-in projection class in Godot 4 that you can pass camera data to and make the projection matrix, but this wonderful class does not show up in any Google search for some reason. So I literally did not find out about this until I was in voice chat in the Godot shaders and VFX server. But of course, being a shader god, I reconstructed the projection matrix using the camera's FOV, near plane and far plane distances. I did not have to Google that, I swear. What? Who even walks around every day remembering how to construct a projection matrix from scratch? If the ray collides with a surface, we'll get the color of the surface and draw it to the screen, and if not, we'll just draw in the background color. To keep things simple and avoid our brain exploding, let's just start out with a sphere. Now that we have a ray and a sphere, we need to do a simple line intersection test. Here's my A-grade math explanation. Take the equations for a sphere and a ray. X is common between both, so we substitute the values. Oh look, this turns out to be a quadratic equation, so we can use the quadratic formula, which has this property known as the discriminant. If the discriminant is greater than 0, then the line intersects at 2 points, meaning it goes straight through the sphere, which counts as a collision. Cool math, now turn it into code. Spend several hours making a GLSL implementation, bang your head on the table, find code online, it's in HLSL of course, spend even more time translating it into GLSL, click play, and it looks like shit. Well, that's because effectively all we're doing is unlit shading. We just collide with the sphere, get its color, and place it on the screen. We're gonna have to do better than that if we plan on impressing Twitter. Well, we have a ray and a ray hit struct that gives us information about the current ray and best collision we have so far. Now that collision information also includes the hit normal, which is actually all we need to do some simple Lambertian diffuse lighting, which is basically just take the dot product of the normal and light vector, clamp it, and multiply it with our unshaded color. Why stop there though? We can practically make a mini fragment shader in here to color up the screen. So let's throw in some specular highlighting using this formula so we get some shiny spheres. To do reflections, we just put our ray tracing code in a for loop so that it traces a bunch more rays and then decrease the opacity of each reflection iteration by how specular the object is. Finally, we can wrap up the Raytracer with some shadow casting, which is just to trace a ray from the collision point towards the light source. And if it hits anything, we darken the color of the pixel so that it's shadowed. But Nekoto, this doesn't actually ray trace any of the meshes in my actual game. First of all, fuck you. Secondly, in order to ray trace the mesh, you have to pass every triangle in the mesh into the computator, do an even more difficult intersection algorithm made by Moller and Trumbor in 1997 on every single triangle that makes up the mesh in-game for every single pixel. Plus, if you want colors and textures, you'll have to pass UVs and material data yourself and practically write your own renderer in a computator. It's not impossible, but it's stupidly difficult. Although a bit dated, in 2014, Scratchapixel made a simple, naive implementation of this in C++, and it took them 15 seconds to render one frame of a cow. There's a reason why AMD and Nvidia are manufacturing GPUs that are specialized in ray tracing. So I definitely wouldn't recommend doing this for an actual game unless Godot brings out its own native ray tracing support. Besides, the purpose of this video was really to teach you about creating and dispatching your own compute shaders. Take a look at this Conway's Game of Life made in Godot 4 with compute shaders. You could even do stuff like GPU clock simulations and so much more. Anyways, if you learned something new from this video or just like it, consider subscribing to my channel. I'm a crazy shader man who loves Godot.